In this video, I will demonstrate how to do a one-sample t-test. In a one-sample t-test, we test whether our expectations of the population mean are reasonable given what we find in a sample of that population. In this demonstration, we will use an example of a study that was interested in the reading ability of young children. In this case, they measured reading speed. They did a study with 26 children, so the sample size is 26. They found a sample mean of 165 words per minute. The standard deviation between children was 21 words per minute. The original hypothesis is that reading speed is 150 words per minute. The alternative hypothesis, H1, is the population mean is larger than 150 words per minute. We will test this with a significance level of 5%. So the question becomes, what are the chances that we would find a sample mean of 165 or more extreme, given that the population mean is 150? If those chances are smaller than a set criterion, the significance level, then we say that this was very unlikely, so unlikely that we do not accept anymore that the population mean was 150. It had to be larger. Let's see if we can find out how to do this. We start with writing down the numbers that we need. The sample size was 26. The sample mean 165. Standard deviation is 21. The hypothesized mean is 150. And we will test with a significance level of 5%. The first thing that we will do very quickly is calculate the standard error. The standard error was the standard deviation divided by the square root of n. In this case, 21 divided by the square root of 26, which would be 4,118. First, we draw up our hypotheses. H0, mu is 150 against the alternative hypothesis that mu is larger than 150. Step 2. We draw the situation. This would be the sampling distribution. At the center, we put the hypothesized population mean. Every time we do a sample, it will end up somewhere here. This is a t-distribution, so we could also write on the horizontal axis the t-values. In case the sample mean is the same as the hypothesized population mean, we would end up with a t-score of 0. So on this axis we have t, and that would be the sample mean minus the hypothesized population mean divided by the standard error. In this case, we found a sample mean of 165. Let's say it is there. It was larger than the hypothesized mean. The question we ask is, what are the probabilities that we would have found a sample mean of 165 or larger? So that would be this probability. Remember, this actually is a histogram. 100% of all possible sample means will be included in this histogram. We are looking at what the probability is that we would end up with a probability or with a sample mean in this area, 165 or larger. Step 3. We calculate the t-value. The t-value for, in this case, with degrees of freedom n-1, which will be 26 minus 1, is the sample mean minus the hypothesized mean divided by the standard error. Therefore, 165 minus the hypothesized mean of 150 divided by the standard error, 4.118. That is a value of 3.642. In the book on page 745, we can look up the probability that we would find a certain t-value or larger. So we're looking for the blue area. We had degrees of freedom of 25. We look that up in the top row. We'll have to move to the next page and then to the next. So we end up on page 747 in the column that says 25. We will then look up the t-value that we found. T would be 3.6, degrees of freedom 25. Therefore, we end up with a value, a p-value of 0.001. So step 4, We have looked up the value of p in the table, and we found that the p-value was smaller than 0.001. Usually we use smaller than or smaller than equal instead of the equal sign, because this is actually an upper limit of our estimation. Step 5, we report the results of our test. T25 is 3.642, and the p-value that goes with that is smaller or equal to 0.001. Because p is smaller than our criterion, our significance level, alpha, we say this sample mean was too unlikely to come from a population mean of 150. Therefore, we reject H0 and we accept the alternative hypothesis that mu is larger than 150. Now what if our hypothesis was not that mu was larger, but mu was different from 150? We call this a two-tailed test. Let's first write down the hypotheses again. We start with H0, mu is 150. H1, the alternative hypothesis, mu does not equal 150. Let's draw the situation. This would be the sample distribution, and mu would be in the middle again. We also know our sample mean would be there. We are now looking for the probabilities on both sides. So we're looking for the probability of this happening and on the other side. Like that. So that would be more extreme than the sample mean. Either positive or negative, doesn't matter. T-value is still the same. That did not change. So it's still 3.642. The p-value on this side is still what we found in the one-tailed test. But now basically we have to double it. Therefore, the p-value is smaller or equal to 2 times 0.001. And that would, of course, be 0.002. In this case, the p-value is still much smaller than our criterion, our significance level of 5%. Therefore, smaller alpha, therefore reject H0, accept H1. The population mean is very unlikely to be 150.